So, hello, good morning everybody. Let us begin our lecture. So before we start, let us recap where are we so far and how close are neural networks at this point for us. Yes, so specifically what we discussed last time was a multi-parameter linear regression, which accordingly can be described in schematic way as this addition of the different features multiplied by their corresponding coefficients, like theta 0, theta 1, theta 2, theta 3, theta 4, and so on. And here, accordingly, we have certain inputs. So theta 0 is always multiplied by bias, 1. Here we have x 1. Here we have x2. Here we have x3, x4, and so on. So at this point we have almost one neuron. Almost, because it's not complete yet. What we need in addition to that is something called an activation, which we don't have yet. Yes, so activation function. But we will add one today, and the main reason why we may need this activation function is sometimes you really have to somehow convert your output into more convenient, we can say, way for the neural network to operate. Yes, because as if right now, if we speak about this part of linear regression, this is going to be in a range from minus infinity to plus infinity, which is too large range. Yes, it depends on your problem, of course. What is your linear regression predicting? Like maybe it's predicting like some small disturbance in I don't know, gravitation force. Yes, or it's predicting billions of profit for your company. So its scale matters on your problem as well. But in a sense, activation function does a little bit more than that, than simply converts. So we'll see today what exactly it does and why we need. So after this class, we will have our single neuron, which will allow us to go further. So today we'll have also with one of group's practical exercise on multi-parameter linear regression and single parameter in one go, and I will show you how you can make the program universal, and then accordingly we are going to improve that program further on. So first of all, to begin today's lecture, we'll now focus on another kind of tasks when you need to basically say classify pictures. For example, you have pictures of handwritten digits. That will be one of our data sets. In fact, we will train neural network on this kind of data set. So you have some picture and it is having written number 1 in hand. Then you have another picture also with number 1, which will look like maybe, I don't know, somehow like this. Another picture of 1 may look even somehow like this or like this. Yes, all of them are pictures of 1 and all of them needs to be identified properly. And beyond that, you will also have pictures 2, 3, 4, etc. all the way up to 0. Yes, so we will try to make a classification problem. Now, different from a linear regression problem, where output was any number in a range from minus infinity to plus infinity, here we have a limited number of possible outcomes, number of certain classes. Yes, so for example, such as simple yes or no when you make prediction, let's say if your email is a spam or not. So as you know, most of our email service providers can filter emails automatically based on spam or not spam, and for that you need to make some kind of a classification, and that's where artificial intelligence comes in. That's where this logistic regression problem can be used. So these classification problems can be binary, as of simply when you try to say is this true or not, yes, or they can be multi-class when you need to have multiple possible outcomes, such as, let's say, pictures of different objects, or maybe categories of email, like work, like promotion, like, I don't know, some bills, etc., etc., yes? And accordingly, this is kind of problems called classification problems, yes? And today we are going to learn how we are going to solve this kind of problems based, of course, on what you already know. So it will be maybe at some point an even surprise for you that we are actually going to use the very same formulas we have used for linear regression and convert this into a problem of classification by simply adding this activation function at the end. And that's basically it. Moreover, this of course should change that derivative we needed to update theta 0, theta 1, etc. But as you will see, even that is not going to change, which is another nice option here. So, first of all, let's focus on the binary kind of problem when you try to predict, for example, is this email spam or not, or I don't know, is this COVID test positive or negative, and so on and so on. Yes, so only two possible outcomes like yes or no are possible. In such condition, we can say that we have two classes. One is a negative class when event didn't happen, and another one is a positive class when the event actually happens. And let's say our model should be able to predict when it happens, yes? There is of course more to that, which we will discuss also in more details in further lectures, and we will try in practical exercises as to what's more important to actually find when it didn't happen, like cyber attack, yes, to have a false alarm or to miss the actual attack, yes. So that is also something we'll discuss in future. But right now, let us say that our data set contains both of these classes, positive and negative, in equal amount. So there is just as many spam as normal messages, which is of course usually not so true. Yes, but for simplicity, we are going to assume that both of these classes are equally represented in your data. So, and then we say one of these classes is going to have a label of 0, another class of these going to have a label of 1. And we want to try to predict if the event happened or not. Yes? So, for this kind of task, we can also use a linear regression as well, no problems, yes? So basically here you can see some of the, how you can say, data set, which is different data set than we used before, but this is actually one of the data sets, one of the groups we'll use today, yes? Like, what is the probability of the student to be admitted to some, I don't know, PhD degree program, let's say, yes, based on different parameters, like what is his mean score in different courses, what is his language knowledge, English, yes, what kind of university did he graduate, yes, does he have a certain research ongoing already, yes or no, yes, and etc., etc. And based on that, the algorithm is going to calculate the probability of the student getting the funds to study further in PhD program. For example, this kind of problem, yes? Now, this kind of problem can be solved in two ways. You can use either linear regression for this kind of task, which we already know. In that case, you are going to predict this as a number, yes? Or you can try to solve this as a classification task. In that case, it's going to say basically yes or no. So here, for example, it's going to be like yes, probably yes, probably yes, probably yes. I don't know, yes or no. Yes, 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 again, maybe no, for example. Yes, so not like some number like probability 0.6, but a plain simple answer, yes or no. Yes, so this changes your output. So let's say for this we try to use this linear kind of regression. This is oversimplified. Let's say we take only one parameter as important. Say, for example, does a student have a research or not? Yes, 1 or 0. And accordingly, well, no, this is not actually true. So here on x-axis, let's say we have as an important parameter some kind of, let's say, score. Yes, this seems reasonable. So we'll try to judge yes or no only solely based on this score column, and that's it. So what we do is then we mark all the score values. So this score, this, 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 and this, and accordingly put the data from our table, which we already have collected, yes, because this is data set you already have, yes, and you already know that the certain person was admitted or was not. And what you try to do is to create an algorithm that will be able in future for next students having this data, but haven't been decided yet, was he admitted or not, to predict will he be accepted with his parameters or not, yes? So this is the kind of problem we try to solve. And here, let's say, x-axis has score, y-axis has the admitted, yes or no. So as you can see, we can basically find the linear function again by trying to minimize the cost so that it is optimal for all of these points. This won't be too good of the solution, maybe some others, because you can see here that actually we have to consider now how are we going to say if it is yes or no from this line. Basically, this line will go in range from some, let's say, 0 to 1, and accordingly, what is yes and what is no on this range, yes? It's quite simple, actually, considering that both of these probabilities are, well, equal in a sense, yes? We can say that we can have certain mean threshold of 0.5. So any number above 0.5 here is going to be considered as a yes. Any number below is going to be considered as no. In that sense, this actually works correctly. Yes, it makes correct predictions. And in a sense, then output can be considered as a probability of being accepted, except that this kind of model will easily say that probability may be 1.5, yes, which of course you know cannot be true because probability is capped at 1. But that's a little bit technical aspect, yes, which you have to filter out yourself. Now let's say we have one very extraordinary, super genius student who managed to get a super high score. Yes, like here. Of course, he will be admitted. That is no doubt about that. But the problem here you can see is that this is going to change this entire line, this entire function, and it might start working not so accurately. Because here we have this 0.5 level, and those students, according to the data statistics, were actually admitted, but based on this prediction, they are not going to make it because they are below this threshold here, just because of this extraordinary outlying data point. Yes, so adding some kind of new data might actually, you know, not really spoil, but make your function not so accurate anymore once you add some more data. So because of that, this kind of a function is really sensible to how much your data actually change on its own scale, yes, from minimum to maximum. What is the maximum deviation from minimum? So in this example, you can clearly see that adding this one extra point actually makes this to be considered as no, where in fact they were yes, yes. So why is that? This is basically because we would like some other way of making this decision. And for that, we are going to introduce a logistic function as an activation function, which we are going to apply to our cost function, so that now we will have a decision boundary as a vertical line, which will then accordingly will not matter anymore if you do have this point or you do not have this point. This vertical line is not going to change because of adding that one extra point, yes? Where it was, it will stay and it will be accurate as it was, yes? So how are we supposed to construct this kind of function then? Well, that of course means that we need another hypothesis, a new hypothesis, in this case called a logistic regression. Yes. Now, logistic basically is a term from probability theory. Yes. So I already mentioned yesterday for one of the groups that we will have different kind of distributions, like normal distribution, like Pareto distribution or uniform distribution, and one of the possible distributions is actually a logistic distribution, which is very similar to normal distribution. Yes. And in fact, I will return to this topic when we'll speak on probability theory then. But it has slightly different parameters, different variance, different mean, etc., etc. So in a sense, we can say that we apply this distribution to our output function. Yes. So we change our hypothesis now to be simply as yes or no, or again, it's going to be, rather than that, certain probability of a yes. Yes. So how exactly are we going to modify our hypothesis then? So, as before, this is our original hypothesis we had so far, yes, in brackets. So it's not really changing much, yes. You still have this theta 0 plus theta 1 x 1I plus theta 2 x 2I plus etc., etc. The only difference now is that after you calculate this hypothesis, you are going to additionally use this activation function on top of that, which of course is going to change your hypothesis entirely. And the goal for us is to compress the output, which is possible for this kind of a formula from, so this is your h theta, yes, from minus infinity as a minimum up to the plus infinity as a maximum, yes, which is basically true if you decide, let's say, to continue this line infinitely. So I can actually draw this line all the way up to the plus infinity eventually. It's going to take forever for me, of course, but technically, sometime this line is going to achieve minus infinity and it is going to achieve plus infinity. It's only a matter of question, how long do I have to draw it, yes? Well, infinity again, of course. So this is not what we like, because we clearly know that our output is restricted to having 0 or 1. So we are going to compress that range from minus infinity to plus infinity to the range from 0 to 1. Again, so that minus infinity matches 0, plus infinity matches 1, and everything that in between gradually increases from 0 to 1. So all that range from minus infinity to plus infinity concentrated in the range from 0 to 1. This is actually quite simple to do. Yes, here you can see this kind of a function that does it for you. So your x value can have any number, so all the way from minus infinity to plus infinity, but your output is going to be capped either by 0 or by 1, yes? So this is a sigmoid function, yes? When you will learn more about probability theory, you will actually see this slightly different way, that this is a probability, this is a cumulative probability function, yes, which we will of course also discuss in probability theory practical exercises, but for this certain point, yes, it doesn't really matter as much, but I can tell you that there is a good solid mathematical reason behind having this sigmoid involved here, yes. And of course, this is the actual mathematical formula of this sigmoid function, which is easy to verify. So if you put z equal to minus infinity, then you are going to get here e at the power of plus infinity, which is infinity, and you divide 1 by infinity, you are approaching, so that's a limit for 0, yes, at minus infinity. Likewise, if you have plus infinity, then you get e power of minus infinity, which is then approaching to 0, and your total expression is approaching to 1. Yes, so this actually works. And in that sense, you can even see that actually we get this 0 and 1 much, much faster than at infinity. Because we could have, argued that there are multiple ways for this function to be constructed. We could also make this kind of a function, let's say, yes. Why not? This is one of the options. Another way of the options would be to make it much slower. No, that's incorrect. So let's try to draw from here. This is also an option, but for a certain reason, justified mathematically, of course, we decided to use specifically a sigmoid function, which is this one, yes? And this corresponds to the logistic function, because others were not necessarily logistic functions. They could be normal functions, they could be other functions. In a sense, we can say that we have certain family of the logistic functions, and this is just one of the possible logistic functions, which we are going to use because it provides a certain benefit for our derivative. Keep in mind that when you calculate this gradient descent method, you will have to calculate derivative of that function. And it turns out that this specific function is convenient for calculating derivative. And in fact, it's going to have you exactly same derivative for the cost function as it was in linear case. So basically you added one extra function, but your derivative did not change because of that, meaning that the speed how your theta parameters changes also won't change. This is very convenient for us. So I'm explaining this from a practical point of view, maybe not really mathematical, but once we get to calculate the derivative, I will specifically return to previous lecture and show you that actually formula is exactly the same, although the problem is different now, yes? Which is why we use specifically this kind of a function, not 2e, not 3e, not 2 plus 2e, not any other kind, but this kind of a function specifically because it's convenient for our derivative, yes? And in a certain way, we have some freedom to choose here, yes? So if we can choose, then we are going to choose what is more convenient. So putting that all together, now our hypothesis is going to look like this, yes, where you can see this ratio as a sigmoid function, and accordingly this power indicator as our old hypothesis. Yes? So putting that all together makes our hypothesis formula like so. And just because of this reason, now we no longer have a mathematically accurate solution like we did in linear regression when you had, well, actually it's easier probably to show it again. When you had this normal equation formula, this kind of a formula, yes, which worked for linear regression. Sadly, for logistic regression, this formula is no longer a valid option. There doesn't exist such kind of a solution, so we are out of options, but only to use a gradient descent or similar methods to find a solution. It's just like I said, only for such kind of a simple problem like linear regression, this formula will work. For logistic regression, no longer. And that is why we decided to use this formula and gradient descent to actually verify that we are doing everything correctly, because your search procedure is not going to change in any way for the logistic regression. So meaning that if your linear regression worked correctly, your logistic regression in part of finding a solution, of course, because you will still have to calculate the sigmoid, put everything correctly, change hypothesis, change the cost function, do a lot of stuff, but the search, the gradient method function, is not going to change in any way for your logistic regression compared to what you had for linear regression, which is again a high convenience. So now the hypothesis actually returns the probability as an answer. So it doesn't say you specifically yes or no, it says you what is the probability of yes, like 78% that it is yes, or 10% that this is yes. And then it is up to you to decide what is your threshold when you are considering this probability to be true and when false. So basically it depends on the distribution of your answers. So let's say you have this kind of a binary problem where you have let's say, 1,000 of possible, I don't know, examples or rows in dataset. Out of them, 500 are yes, and 500 are no. In that case, when your hypothesis says something like, no, this is not hypothesis, something like 0.67, you need to decide, is this yes or no? Since you have equal amount of this yes or no, you can then say that you are going to compare it with 0.5, and accordingly, if it is higher than that, then it is going to be yes. If it is lower than that, then it is going to be no. But there can be situations when you might choose not 0.5, but some kind of other number. So let's say you have certain rare events, yes, of something not happening, or maybe vice versa. Let's say you are trying to predict some kind of a cyber attack, and there is a lot more of normal data than of actual cyber attack happening. So in that case, you might want to actually tune up this number, maybe to 0.1, maybe to 0.2. So again, it's not as simple to choose, yes? But for majority of cases, we are going to have 0.5 just because, well, both events are equally probable, yes, and based on that, we can actually then just to basically round this number, yes? So if it's more than 0.5, it's going to be rounded to 1. If it is less than 0.5, then it is going to be rounded to 0. So as simple as that. In that sense, we can then write that this probability, yes, of the event to happen for certain theta parameters, because these again theta parameters are what we don't know, what we need to find by using the gradient descent method, is our hypothesis. So your hypothesis is the probability of event happening being true, yes, which we are then trying to predict. So now let's say you have two possible input parameters, x1 and x2, yes, and then you have certain criteria to match, yes. And what we need to do is to find certain boundary between these two classes, yes, in kind of a line splitting these two clusters of data. Yes, and accordingly, if your predicted point is going to be above this line, then this is going to be class 1, let's say 1, yes. If it is below, then it is going to be class 0. Basically as simple as that. So mathematically, again, we need to construct the line with correct parameters, theta 0, theta 1, and theta 2, and then to find the solution. Yes. So at this point, we can say that theta 0 is -3, theta 1 is +1, and theta 2 is also +1. So this is theta 0, this is theta 1, and this is theta 2. So here I am using now vector form, yes, which we discussed on the previous lecture, but still try to remind you that this is actually a vector consisting of the same theta 0, theta 1, theta 2, which we used before. So we simply put those numbers in, get this accurate hypothesis, and now we need to see when it is actually positive. Yes, so for that to happen, we can then move this -3 here, yes, and the condition to have y equal to 1 will be x1 plus x2 together are at least 3, yes, which is basically this line. Well, if I can, I try to draw it more accurately, but it goes through this point, yes, when x1 is 0, x2 is 3, so together they are 3, and this is yes, and accordingly x1 is 3 and x2 is 0. So basically I put 2 points, yes, x1 is equal to 0, x2 is equal to 3, which is true for this condition, yes, and that is this point. Another point is opposite. x1 is equal 3, x2 is equal 0, which is this point. And then you simply connect with a straight line these 2 points, because you know the straight line has only 2 points at least to be constructed. Yes, and you get this solution in graphical form as well. So then we apply a sigmoid function to this expression, yes, to get it converted to yes or no, which is this function. Now, there is one other thing to mention here, that you are actually not really restricted. Yes?
I don't understand why is y equal to 1
Why did they choose these numbers? Yes?
yes, and for the prediction, y equals to 1.
Ah, well, it is like we say, because probably I didn't mention this, yes, but we assume that x is 1 and that this blue dot is 0. Yes? So the red cross has to be above this line, right? They are above. And since our red cross is 1, so that is the case. We need to have predicted a red cross, yes, which is y equal to 1, and that happens only if this is at least 0, yes? No? Not entirely understand?
Just fix it, we could say equals to, if it was...
No, there are only 2 possible outcomes. It can be 0 or it can be 1. Yes or no. So accordingly, what we are trying to make here is our hypothesis: is this a cross? There are only possible 2 answers to this question. Yes, which is 1, or no, which is 0. Yes, this is a binary problem. Like no 2, no 3, no nothing. Yes, so accordingly, if we are interested to find yes, then it has to be cross, because this is the scenario we are now studying, yes, and all the crosses are above this line. Now this formula is the equation of this line, so we are interested to know all the points that are more than this equation, so positive, yes, and for those points it's going to be 0. Likewise, we could say also that for y equals 0, yes, we say that happens if minus 3 plus x1 plus x2 is less than 0. So it will happen to be if this inequality is less than 0, not at least equal. So likewise, then we can say that if x1 plus x2 is less than 3, then y is going to be 0. And there is no like anything in between them. It is either 0 or 1. Not like 0.5, not like 0.99, just, you know, discrete set of outputs, which is not exactly so for this linear hypothesis, because this actual linear hypothesis, as you can see, can have different values of 3, of, well, it's not exactly this line. We need to construct it in some kind of 3-dimensional space, but it's clearly not just 1 and 0. It's an entire linear function having different values. So here it is 3, here it is 0, yes, here it is maybe somewhere 2, 1, etc. And we need to convert that by using this sigmoid function. That's why we have this g here. So why it is 1? Just because I wanted to predict crosses. Yes, if I wanted to predict circles, I would say y is equal 0. And there are no other options at here, because we simply do not have any other shapes, which we will fix later on. Don't worry, we will have 1, 2, 3, and all the way up to 10. But at this point, it's just for simplicity 2 possible outcomes. So as I mentioned then, linear boundary, boundary is this line separating these two clusters of data. Yes, it does not really have to be a straight line. It doesn't really have to be a linear function. You can easily use a polynomial hypothesis as well. In that case, it's going to look like this. Yes, so you are going to have g as a sigmoid function of theta 0 plus, let's say, theta 1 x1 plus theta 2 x1 square plus theta 3 x2 plus theta 4 x2 square. So in that case, now it is a polynomial regression, which works just the same, and it will construct some kind of a polynomial line, yes? It doesn't really have to be just a linear regression. And as we discussed in previous lecture, it is very simple to convert linear regression into nonlinear regression by simply intentionally changing some of the data. Yes, let me return back here. Like here, originally I had only weight as input, but then I decided, let me calculate the square of the weight. This was my own initiative to do it. I didn't have this data, but it's not difficult to do. Yes, if you have some numbers, you can always calculate square for them. This way now I have this as x and this as x squared, and the hypothesis becomes nonlinear. Yes, so it's as simple as that, which you can also force put here in these brackets as well. So now, back to the question. So for linear regression, our ultimate goal was to find theta 0, theta 1, theta 2, theta 3. Here, it's not going to be any different. This is exactly the same kind of procedure we need to go. And so let's see what actually changes from linear regression in this case of logistic regression. Obviously, we are going to need another kind of a cost function, because now our outcomes is just 0 and 1, and well, we don't really want to calculate any wrong predictions, yes? So that is the starting point. We need another kind of a cost function for this. And because we are going to change the cost function, we are going to need a derivative of this cost function for theta 0, derivative for theta 1, and so on. But then, otherwise, the method is exactly the same. You are still going to use the gradient descent method, which we discussed in previous lectures, yes. This kind of a method, yes. The only thing is that now your derivative might change, but as I already have mentioned, it will remain the same. And absolutely definitely, your hypothesis already has changed, and your cost function also needs to change. So let us go through these changes, what exactly changes and how. Let us also calculate, not really calculate, but more like, get expressions for the derivative to prove that it's actually the same, and then accordingly we'll be able to summarize this and say what is going to change if you are going to predict like not only 2 possible cases but 3, 4 or more. So again, the basically feedback algorithm gets to understand how good or bad is his prediction is this cost function. So the cost function is this sense of the algorithm to understand how well it is doing. So that is very important in all kinds of problems, to specify this cost function correctly. Now our previous cost function we were using, which I can again write here, yes. Divided by 2m, was hypothesis minus real answers. Is not really useful here anymore, directly at least, yes, for various reasons, yes. Well, mainly because your hypothesis also is going to be either 1 or 0, and your y is either 1 or 0. We could try and use this cost function, but it will not, how you can say, help to understand how big is error, yes? So you either are going to get here or either 0 if you guessed correctly, or well, 1 basically, if you guessed incorrectly. But there is no way to understand how close you were to actually correct answer, judging by this one. You could have made a huge error, or you could have made a tiny, tiny little error, and in both cases the cost function will say just 1, yes? So, like, I don't know, let's say you are coming to me with your project and I need to grade it, and accordingly I will say it's either 0 or 10, yes? And you cannot understand, is it your normal project or bad project because you didn't get 10 because it wasn't amazing, yes? And this way, there is no way for you to understand how bad or how good is your project actually, yes? So you for that need to grade it from 0 to 10, like 1, 2, 3, and also on. So similarly here as well, having this 1 for any kind of error doesn't really help us. We need to have more accurate saying that, okay, your error is maybe 25% or maybe 70% or maybe 1,000,000,000%, yes, for algorithm to understand how it needs to fix theta 1, theta 2, and so on and so on. So, because of that, we are going to change this cost function like so. Yes. So what is happening here is now that our cost function has to be conditional. Yes, there will be 2 conditions. So if here y is actually real answer. Yes, so if the real answer was yes, then you calculate a cost function according to this function. If the real answer was no, you are going to calculate cost function according to this expression. So what do we have here inside? Yes, inside what we are basically doing here is calculating the logarithm of hypothesis, and with a minus sign, because, well, your hypothesis is now in range from 0 to 1, and the logarithm of any base, I don't know, some base a, of this number h will be negative, yes? We don't want our cost function to be negative, because, well, in that sense, having minus this number is much better than having minus 1, yes? Because this is a smaller number, so the cost function, the algorithm will think, okay, my cost function actually can be reduced up to minus infinity. That will be the perfect solution, which is not true, yes? We want to have absolute value. And if we speak about absolute value, then 1, of course, is much better than 1,000,000, or yes, 1,000,000, yes? So to avoid this, we put this minus sign to compensate for the fact that logarithm is going to be negative and that is going to become positive. And as to what changes here, yes, is quite simple, really, yes? So when you try to predict 0, yes, you take the opposite event. And since this is the probability, and you have a probability of finding yes, and you need to know what is the probability of finding no, you simply take the complement of this probability, yes, by calculating 1 minus probability, and that is the probability of the opposite event. Otherwise, this formula is the same, it's just we are focused only on the positive outcome, yes, on y equal to 1. And if it happens to be not, then we are going to use this kind of a formula. Now, we can actually put these 2 expressions into one single cost function. Like here you can see these 2 logarithms visualized as plots, yes, and accordingly you can see that the closer you are to guessing correctly, so here if you guessed correctly, and here if you guess completely opposite, completely incorrectly. And here, as I said, you have certain gradation, yes, like almost correctly, well, basically correctly, too incorrectly, etc., etc. So here you can see how much was your error by this plot, other than linear regressions simply correct or wrong, yes? So here you can see how correct and how wrong you were for predicting 1. And accordingly here, as you can see, what we are doing is predicting 0, yes? So if the actual answer is 0 and you try to predict 0, then you will have a minimum cost function at this point, yes? And if you predicted 1 when it was actually 0, your cost function is going to be much, much, much more, yes? So these are opposite. Now, as I say, we can put these two expressions into one formula so that we don't have to program some kind of if, yes, because here it says specifically if y is 1, then this, if y is 0, then that, which is not good practice for us, especially considering we want to vectorize this solution, and it will be difficult to do so with if, yes. So in a sense then, what we are going to say here is that we are going to combine them together into one formula by adding certain factor. So here you can see this part, and here you can see this part, yes? And how are we going to make it so that if y is equal to 1, only this part will be calculated and this will be omitted? Well, very simple. As you can see here, we have added this factor of y, and y can be either 0 or 1. So the hypothesis h theta can be any number in range from 0 to 1, but the actual answer y can be only 0 and only 1. So if y is 1, then what happens here is that we put here 1, we put here 1, we get this bracket equal to 0, 0 is multiplied by this logarithm and cancels it out. And this one stays. Yes, very simple as that. If actually y is going to be 0, it will work opposite way. So if y is 0, here we put 0, we cancel out this part, here we put 0, it becomes 1, and this part is kept. Yes? So this way, because your y can be either 1 or 0, we can actually combine them into single expression and have this formula as a cost function. So this is formula for our cost function for logistic regression, which is slightly different. And as I said, we do so because we want to understand how good or how bad is our prediction. Not like a simple category, good or bad, but how exactly good, like how far we were from the correct answer, basically, yes? More detailed. If that, then what we need to do now is to have this cost function minimized for certain theta 0, theta 1, theta 2, theta 3 parameters. So the problem statement is exactly the same as it was for linear regression, except that now you need to minimize another kind of function. And also please notice that I have put this minus sign outside of these brackets, because here we had minus logarithm, here we had minus logarithm, and I put this minus sign outside of brackets. Here we have plus. Also notice that here we have just plain m, not 2m, but simply m. Again, it's necessary for getting the correct derivative. So the idea is exactly the same as it was before. You start with some theta 0, let's say 0, theta 1, say 0, theta 2, say 0, and then you improve this solution by running multiple iterations accordingly for all theta parameters by subtracting this alpha learning rate multiplied by the derivative of cost function. Now, however, your cost function is different, and technically you should now find this derivative of this cost function. As I said, it's going to be the same, surprisingly, yes, because this formula is completely different from the cost function of linear regression, which was this formula, yes. So how is it then possible that having derivative for theta 0, theta 1, and all of them, actually all of them, yes, is going to be exactly the same for this formula and for this formula, if these formulas are actually different. Well, it can happen, and it happens so because we have selected specific sigmoid function, yes, we have used m here, not double m, and all the other details. When I said because we have a freedom to do so, we do so, yes, just to have this as an answer. So now let's try and get this derivative calculated for any arbitrary theta j parameter. So I won't go like separated formula for theta 0 or separate formula for theta 1, because the procedure will be the same for all of them. Yes, so now you need to calculate this cost function. And also keep in mind that your h theta at this point is 1 divided by 1 plus e minus theta 0 minus theta 1 x1 minus theta 2 x2, etc., etc. So this is how your hypothesis looks like. And on top of that, you also calculate logarithm of that, and you will have to calculate derivative of all that stuff. Even I think, need some assisting table of different derivative functions, yes, to go formulas, yes, to go through these. So we are going to need yes, what it is, cosine. We are going to need some logarithm formulas. No, here not. Let's find another table. Here, power. Nope. Just a moment, just a moment. Here it is. Yes? So we are going to need, first of all, the power formulas and also the logarithm formulas. Yes? Well, it turns out that these are actually very simple formulas, because calculating the logarithm of power is this same power, and calculating logarithm, yes, the ln x is 1 versus x. But also keep in mind that here you have not simply x, but entire expression, which you then are going to need to open further. So let's try and go through. Again, this might be a little bit difficult for somebody, maybe a little bit boring, or maybe not a little bit boring, but I just want to get it done, yes, to explain this, so that in case you are going to need to somehow verify this, you have knowledge how to do it, yes? So what we are going to do is, first of all, to remember that calculating derivative of a constant, of summation, doesn't really change anything. So you can calculate derivative either this way, or this way. Yes, and it's going to be exactly the same. So this summation really works. Then furthermore, you can actually put this a outside and this b also as well, because this is a constant, which we do here as well with this minus and all that other stuff. So with that in mind, what we need to do now is to calculate separately this logarithm derivative and separately this one. Yes. First, I actually have calculated them both here already. Yes. So what happened at this step is I didn't change these. Well, because it doesn't depend on any theta. This is just a constant. So I calculated this logarithm derivative. Yes, which happens to be 1 divided by this h theta multiplied by derivative of this h theta. Yes? So this is what you can see here, that we have calculated the derivative of the logarithm itself, and then we need to calculate derivative of the what this logarithm is calculated from, of the brackets, of the argument of the logarithm. Similarly, it works for 1 minus logarithm. Yes, so here you have 1 minus h theta, and here you have h theta as well, because calculating the derivative of 1 minus x, yes, is actually simply calculating derivative of x. Because derivative of 1 is 0, it's a constant, yes? So we could say that here we have 0 plus this one, yes? But 0 I didn't write it here. So what we need to do now, in a sense, is just to calculate the hypothesis derivative and put it in the correct place, yes? We can do that separately, what we are doing here. So let me remind you that the hypothesis was uh, 1 versus minus theta transposed x. So this is in a matrix form, yes. So in that case, when you need to calculate some kind of a function like this, yes, derivative of 1 divided by x, you are going to end up with having this as a minus 1 divided by x squared. Yes, this is again one of the rules of the derivatives. Let's see if the table shows it. Yes, it does. It's the first rule here. So if you calculate of some power, and 1 divided by x can be represented as x at the power of minus 1, let me remind you, yes? So then you have to put this n in front, which is minus 1 multiplied by x at the power of minus 2, which is minus 1 divided by x squared, yes? So it is correct. Furthermore, then, we need to continue this derivative. Now we are going to calculate the derivative of the argument of what we have calculated here, of this particular part. Again, calculating derivative of 1 is just 0, so it's not changing anything, and all that we need to calculate derivative of is this exponential, yes? So that is this part. Again, calculating derivative of the exponent is trivial. Yes, calculating it derivative of e power of ax is eax multiplied by a. Yes, so in our sense, then here it is. Yes, e of the power multiplied, well, actually, well, here we have to really put derivative of the x, well, because this particular one is 1, but in general, this x can be any kind of a function of x, like some kind of a function of x, yes, which then you are going to calculate derivative for. So here you have this e power of this, yes, and here you have the power of the derivative of the power indicator of this e power of x, yes, minus theta t of x. Now, let me remind you that your minus theta multiplied by x is actually minus theta 0, minus theta 1 x1, minus etc., minus theta j xj, minus etc., etc. So when you calculate derivative versus theta j, all the others are considered constant and only this one remains. And calculating theta j xj derivative versus theta j returns you simply xj. Yes, because this becomes a linear. With a minus sign, of course. So this is our final answer, which we can then a little bit, improve by putting the minus signs together, this minus sign, and also moving this in the numerator. So then your expression looks like this. How is this derivative similar to the derivative of the linear regression, you might ask, yes? because what I am claiming is this stuff, what we have obtained here, is exactly same as here. Well, let's see if we can make it. Yes, sorry, this is not the final answer yet. This is just a derivative of the hypothesis. I'm a little bit running ahead of time. Yes, which we are now going to put inside of this expression we have here. So this, what we have calculated, needs to go here and here. Yes, so you put that in, substitute it back into our derivative expression, which happens to be here. Yes, so we substitute this here and here. Also, I write down the hypothesis as well. Yes. Wait, how to better explain what happens here? Okay, maybe I just need some extra line explained here. So let's say, how did I obtain this part? Well, I have my formula saying here hypothesis. My hypothesis is so hypothesis is 1 versus 1 plus E minus theta transpose X. I have this yi, which is a constant, and sorry, not here, but it's here. And then I put this expression here. So E minus theta transposed X, 1 plus E minus theta transposed X squared. Yes? So what happens now is that I can see that this part and this part are the same. So I can simply cancel out it here, and then I will have not a square but a 1, which is exactly what you see here. Similarly, it goes for the second part. Yes? So what we have here now is this kind of expression. And what we can do further is open these brackets. Yes? To have it separated. Because this denominator and this denominator is exactly same, we can actually even factor out something from here. So doing that, here we have it. Yes, open the brackets. These brackets were originally like here, except that here it was minus and here it was minus, so I have replaced this by plus and changed order. Yes, so here you can see 1 and here you can see y. Yes, so I changed order because I changed the sign to plus and it was originally minus. And then we can see that actually now we have here yi, you have here yi, and we can merge them together. Yes? Merging them together will give you 1, well, not 1, but let's write in the same order as it was, E minus theta transposed X plus 1. Here you have 1 plus E minus theta transposed X, which is 1. Yes? So you are left with this yi and this xj. Whereas this is our actual hypothesis. Multiplied by x. Yes, here also x. Factoring out this xj outside of the brackets gives you the final expression, hypothesis minus yi multiplied by xj. And this is exactly the same, as I've said, what we had for a linear regression. Yes, so let me try to show them Can I show them separately? I can. Side by side somehow. Increase size here and increase size here. Yes? Well, we are speaking about this part particularly right now without theta 4 minus this. Alpha versus m, hypothesis, minus y, multiplied by xj, multiplied by xj. Exactly same answer, but completely different way and much more complicated than it was before. So as you can see, just adding these activation functions has significantly increased difficulty of getting this expression. But for you, it is sufficient to know this formula didn't change at all, yes, from the linear regression. So this gives you right to simply copy-paste the code from our previous practical exercise and use this for logistic regression, which is amazing, yes, for us. Because, well, I don't know about you, but me in particular, I am not math major, yes, so it also takes a lot of time to actually understand this for me as well. So it's just I wanted to go through this and accordingly have it, you know, proven to you. So, okay, concluding this today's lecture, quite mathematically intense, I might add, yes, let's finally say what if now we want to classify not simply in 2 categories like yes or no, but into 3 categories like green triangles, red crosses, or blue squares. Or like for email, is this an email related to your work? Is this for spam? Is this for family? Maybe some promotions, etc., etc. So different kinds of categories. Or for weather, is it sunny, cloudy, snowy? Yes. Or handwritten digits from 0 to 9. A million of possible ways to classify different objects, pictures of computer vision algorithms, yes, like this is a car, this is a bike, this is a traffic sign, and all that stuff. All of them are actually having more than just 2 possible outcomes. So how are we supposed to deal with this kind of problem based on what we already know? Yes? Very simple, actually. We are going to split this one problem into 3 problems and say we are going to create a specialized classifier responsible only for its own part. So instead of trying to make some kind of problem classifying separately triangles, separately squares, separately crosses, we are going to make 3 classifiers. The first classifier will give you the answer to question, yes, triangle. Yes or no. The second classifier is going to give you answer to this, a yes or no. And the third one, just the same way. So we are now making the 3 classifiers we already know, yes, and accordingly each of them is going to, as I said, have its own hypothesis. Yes, so hypothesis of this being a square cross, hypothesis of being square, and hypothesis of being a triangle. Now let me remind you that each of these hypotheses actually returns you a probability from 0 to 1. So meaning that, let's say for this case specifically, I don't know which color to choose, so let's choose something like this. Yes, for this particular point, then we can calculate 3 probabilities. Probability 1 will say that this is a square, no, this is a triangle, yes, so basically probability of this being a triangle will be 0.15. The second hypothesis will say that this is a probability of a square being, let's say 0.75. And the third hypothesis says this is a cross with a probability 0.2. So comparing all these 3 probabilities gives you a very obvious solution that the highest probability is actually true, and this way you know that this is actually a square, yes, because the probability of square is the highest. So it is really as simple as that. You can and create 3 classifiers or 10 classifiers or 100 classifiers, whatever is number of your classes, and each of these classifiers is going to separately be specialized on its own class, yes? We're returning, if this is not a square, then obviously it is either cross or triangle. If we know that this is not a triangle, then only option left is this is a cross. And this way we sort out by finding the maximum probability among all of these 3 cases. So this is specifically the approach called one versus all, which we are going to use to train our algorithm to recognize these handwritten digits. Yes, 1, 2, which 2 may look even like somehow like this, yes, etc., etc. And this will work, you will see by your own eyes, so we will gradually increase complexity of our program, yes, up to the neural network, which you will write completely yourself. So everything in that neural network, well, maybe except that optimization, you could use gradient descent, which you also write on your own, but then we'll have to deal with derivative, which is a little bit out of this course, I believe, at least for your specialty, or even my knowledge, yes. So we will borrow some algorithm to find a solution. So okay, this then concludes today's lecture. Also, I had some question yesterday about how are you supposed to turn in your practical exercises, and for you I have created here links which you can press. So for probability theory we have already with one group 2 exercises, another group will have next week 2nd exercise, but there you have to create 2 reports. And for machine learning, no reports necessary yet. Today we will have the first exercise when you will need to make a report. So I will add similar links for machine learning for every practical exercise. You can either submit them here in this part or in this general tasks section, where you also have some other submissions to do, like tests, final exams, retake, which are probably not visible to you yet, but because I'm an instructor I can see them. But my ones are going to be here, practical exercises on computers. Now these should be visible to you already. You simply press this button, upload file. Then if I don't like something, I leave comments, you can read them, upload another version, and so on. So I will mark them on scale from 0 to 10, yeah, but this doesn't necessarily mean your final grade is going to be same. It's more like for myself, how I grade your work on the report, yes? And I will show you some example of report also next week to get the idea what is expected to be a normal report, yes? So, okay, are there any questions? So, if no questions, then today's lecture is over, and then another group will have a practical exercise at 12:30. Thank you.